Hey, guess what? As of January 8th, 2022, the James Webb Space Telescope is fully deployed. If you love astronomy as much as I do, you must know this is a huge deal. It's a monumental achievement of human engineering for so many reasons. For starters, it's an incredible size. The primary mirror alone is over 21 feet wide. The Hubble Space Telescope, the previous largest eye in space, has a mirror of around 7 feet, 10.5 inches. That's like comparing a horse with an elephant. And there's a good reason for why it was built so huge. The James Webb is not an optical telescope in the traditional sense. It is an infrared telescope, meaning it sees heat. Infrared light has a longer wavelength than visible light, so it needs a larger mirror to focus that light. Now, I could talk all day about the various aspects of the James Webb Space Telescope that make it uniquely exciting, but they can be put into two broad categories: the incredible technology that went into building it, and the incredible discoveries it'll allow us to make. So, let's talk about that. Because of its greater light-gathering power, the James Webb Space Telescope will be able to take images of things that we were never able to see before, but have always wanted to. Things like exoplanets, ancient galaxies, stars and planets forming inside nebulae. And you can bet there's going to be a whole lot of surprises too. To achieve this, the James Webb has several technological tricks up its sleeve. Let's start with the special device called the coronagraph. This is what will allow us to take the first real pictures of exoplanets. What it does is it blocks out the bright pinpoint light of stars, which we already know have planets orbiting around them. Without the coronagraph, the starlight would completely outshine and drown out the light of these planets, because planets are hundreds of thousands of times dimmer than the star. So, with the coronagraph blocking the starlight, the exoplanets come into view. And the James Webb coronagraph can block the light from up to 100 stars at once. So we can expect to find loads of exoplanets. This brings us to the next high-tech gadget, the no-slit spectrograph. Usually, an ordinary spectrograph will have a slit to allow a sliver of light to enter and be diffracted. Diffraction is the scattering of light to reveal the spectrum of light's component wavelengths. But the James Webb's work is so sensitive that a sliver of light would overwhelm the optics. So, a no-slit spectrograph was installed. The starlight gathered from the big mirror is sent into a fiber optic cable to send only a single spot of light into the spectroscope. And that's where the grism takes over. You might have heard of the word prism, like the one Sir Isaac Newton used to discover the spectrum of sunlight. Maybe you've heard the phrase Roy G. Biv? But the Webb instead uses a grism. It's a compound word, like how smog is just, smoke and fog. A grism is a graded prism. That means it's got itty-bitty tiny grooves that diffract the spot of light the big mirror sends down the fiber optic cable and into the spectrograph. The science of reading the spectrum of light is called spectroscopy. By analyzing the spectra of light from the exoplanets, the James Webb will determine what gases are in the planet's atmosphere, as well as their density and even their temperature. We will be able to tell if a planet has oxygen, nitrogen, methane, and any other gases that may or may not indicate that the planet is habitable. Another planet like Earth, perhaps? So, where is it right now? Unlike the Hubble Space Telescope, which orbits the Earth, the James Webb Space Telescope orbits the Sun, currently parked in the exact sweet spot it needs to stay in without having to use barely any fuel to hold its position. There are 5 gravitational balance points between the Sun and the Earth. They are called Lagrange points, named after their discoverer, Joseph Louis Lagrange, in the 18th century. The Webb is parked at L2, the second of the 5 Lagrange points, which lies 932,000 miles out in space, way beyond the moon. All this to observe one spot of infrared light. But first, the engineers must acquire that spot of light. First, the 18 hexagonal mirrors of the telescope had to be unfolded from their position inside the Ariane rocket that sent the Webb into space. Once the mirrors unfolded, their positions had to be adjusted to microscopic level accuracy so that all 18 mirrors produce a single image. Several tiny motors are attached to each mirror segment to make these adjustments. These motors, which were activated individually, gradually pulled the honeycomb-like mirror segment into alignment. This was a critical part of the mission, and it took months to complete. Now, to align the mirrors to produce a single spot of light, the James Webb Space Telescope can't be jiggling around. It must be kept absolutely motionless. And that requires two other cutting-edge technologies, the Sunshield and the cryocooler. In space, direct sunlight is very hot and the shade is very cold. Therefore, the James Webb Space Telescope is equipped with its own high-tech Sunshield. It's huge too, big as a tennis court huge. Comprised of 5 individual layers of Kapton film only a millimeter thick, each layer of the Sunshield had to be remotely deployed individually using a system of 8 motors and 139 actuators with thousands of parts. The purpose of the Sunshield is to help the James stay cold. The colder, the better. And colder is what the cryocooler is for. In science, temperature can be measured in several different ways. In degrees Fahrenheit, where water freezes at 32 degrees and boils at 212, or in degrees Celsius, where water freezes at 0 degrees and boils at 100. But neither of these thermometers have an objective starting point. So Lord Kelvin, in the 19th century, devised a third temperature scale, the Kelvin scale, which starts at absolute 0, the coldest temperature possible. For reference, water freezes at 273.2 degrees Kelvin and boils at 373.2. The onboard cryocooler will cool the James Webb to just 7 degrees Kelvin, 7 degrees above absolute 0. Why is this necessary? Heat is a form of energy which causes movement. The hotter the James Webb would be, the more it would vibrate, shaking the cameras too violently to take any useful images. At the temperature set by the cryocooler, virtually all heat from the motors is removed, and the telescope will be able to focus the light on a single precise point without any motion that would interfere with the quality of the image. Finally, after all this incredible technology operates remotely as planned, we are almost ready to observe the infrared images from the giant multi-segmented mirror of the James Webb Space Telescope. Almost ready. A telescope can collect all the light it wants, but in the end, it must be able to detect what it has collected. If the light is not detected, it's not truly observed. Enter la piste de la résistance, the infrared detectors. The James Webb has 15 of them. They're made of a specially fabricated semiconductor material that produces a slight electrical charge when struck by a photon of infrared light. Each of the James Webb's infrared detectors can produce a 1 million pixel high-def image. A few of them can even go up to 4 million pixels. They must be durable enough to last 10 to 20 years without warping or corrupting, all while working at 7 degrees above absolute 0. In and of themselves, these infrared detectors are an engineering marvel. But I hear you ask from across the screen, what are they going to take pictures of? That is just as exciting. 70 of the first 280 target observations are exoplanets. Is there another Earth-like planet out there? Are there any exoplanets that seem habitable? The James Webb Space Telescope will provide detailed spectroscopic analysis of the atmospheres of thousands of known exoplanets to answer these burning questions. For the very first time, we will see images of exoplanets as they appear in infrared light. But perhaps the primary mission of the James Webb is to provide data for research of questions of cosmology, the study of the universe. The prime targets for observation will be the galaxies at the edge of the universe, receding away so fast that their light is stretched into the infrared. Hundreds of hours of observations are necessary to collect the faint infrared light from these first galaxies formed after the Big Bang. Thus, the James Webb will give us a picture of what the infant universe looked like. Astronomers will also learn new information about the dark energy that is driving the expansion of the universe and what role black holes play in the formation of galaxies, if any. Star formation in the Milky Way and nearby galaxies is also part of the mission. By imaging hundreds of solar systems forming around newborn stars, astronomers will establish a more accurate history of star system development. Now fact will replace theory, and humanity will take a big step forward in our understanding of space. January 8th, 2022. Mark the date in your calendar, because the full deployment of the James Webb Space Telescope might be seen by future historians as the day that a new epoch began in scientific history. I don't know about you, but I'm very excited.